We'll go with 30 seconds.
Okay. All right. Well, hello, everyone in person and online. Please bear with us. We have the smaller room, so thanks for coming in person and are online. So those online, we can hear you through Anika's computer. So if there's issues with the video or sound, just let us know and we'll change it. But today we have an exciting seminar by Anika Schmiedeke. So Anika got her PhD at the University of Cologne in Germany, and she studied 3D radiative transfer modeling of high mass star formation in Sagittarius B2. And then she was a postdoctoral fellow at the Max Planck Institute for Extraterrestrial Physics, MPE, in Barking. And she worked on low mass star formation. And she's mainly interested in low and high star formation, high mass star formation, radiative transfer, and lots of star formation things. So thank you for giving us talk today. We're looking forward to it.
I hope everyone can hear me. I will try not to move too much and move too far away from the microphone, but if I do, especially online, please, I don't know, let me know, shout or something, and we will try to figure something out. So let's see, can I move? No, I cannot move. I can move. Okay. So the process of star formation is a hierarchical process. So in the classical picture, you have these large diffuse clouds within which you have the molecular clouds residing. And then these clouds, these molecular clouds in the top right corner of your screen, they have sizes of 10 parsecs or larger. They collapse with time. So due to turbulence or local instabilities, they start collapsing and forming denser cores within the molecular clouds of sizes of roughly 0.1 parsec. And then these dense cores collapse further in the picture, and you get the protostellar systems of a few hundred AU, and following up with the protoplanetary systems where the planets are then forming in these disks. So if we look at this center, like this bottom part of this cycle a bit closer. This is just a refresher for some of you, and I think because there are many students present as well, and this might not be your field yet, I added this into the slides. So this is the current model of star formation. In these lower parts, once you have the molecular clouds and they're collapsing due to this instability and turbulence, you start forming something that is a gravitationally bound core. We call it then a prestellar core. These are very tiny. You have this infalling, more or less spherical envelope. It continues on into the next stage. So it fragments, no, it doesn't fragment, it collapses and forms the dense central core. This is depicted here with the yellow little spot, that's our protostar. You form a disk around this due to conservation of the angular momentum. And then also you get these outflows that are opening up and opening in the envelope that is further infalling. With time, more material from the envelope is accumulated onto the protostar, and the envelope is more or less either accumulated or dispersed. And then you start having your star and your planet start formed within this disk. So the main constituents for the process of early star formations are our molecular clouds, the dense cores. Wait, why is this already? Yes, here, sorry. The dense cores, the envelopes and the disks. And when going from the molecular clouds to the disks, we are basically covering 5 orders of magnitudes in spatial scales. So we are covering a large dimensions basically, and trying to resolve this. Until basically only recently, these transitions between the scales, as I've shown you before, was more or less assumed to be spherical symmetric in the theory. Everything just spherical symmetric core collapsing and falling and so on. And that was it, basically. But only recently we started to see that this actually might not be the case. So let me show you this. We will start now with the smaller scales with the disk. And I will, yes, it shows up, sorry. I will have the scale sizes, what we are talking about, in the top right corner of your slides. So you always have an idea about which scales we are basically talking on the individual slides. So now we are in the in the smallest scales. There's one object that's located in a few code. It's called IRS-63. This is a class 1 protostar. And back in 2020, we showed that the young disk around this protostar has annular substructure. I hope you can see this here. These are these kind of rings and gaps in the structure. And this is the youngest, or actually I should say this is one of the least evolved disks that has this ring substructure that we found. And this is very reminiscent, if you have seen this in of these HL Tau rings. Just HL Tau is a more evolved disk, but it has these very clear rings and gaps in the disk. For IRS-63, we have actually followed up our continuum study with a molecular line study. We observed H13CO plus with ALMA. And surprisingly, what we found was this streamer-like emission. I'll try to highlight this. So this emission, yeah, you can see the pointer. This emission up here. The important part about this figure as well, so the dotted circle that you see here, that is the primary beam of the ALMA interferometer. So up to there, you can observe the structures. Everything outside, you're basically not sensitive to with an interferometer. So what you see is this streamer-like structure that extends up to the primary beam of the observation. So it's truncated there. It could continue further. We don't know. We would need follow-up observations to observe the extended structure. Yeah, why do we call it a streamer? I mean, this is a moment map, could be just chance alignment, but if we look at the velocity field, you do see this gradient in the velocities from the edge towards the center, circling or spiraling in, if you want, onto the disk structure. The contours that you see here, these are the continuum contours that we do that I've shown you before. Also important to note for these type of sources, this has nothing to do with the outflow angle or with the outflow at all. So this is not streamer caused by the outflow or anything. The outflow is oriented the way I show this here in with the arrows. So the blue lobe and the red lobe. Yeah. Why do I show radiative transporting? Well, back in 2019, so before we published the continuum study of that paper, Dominique, the author of the first author of that paper, and me, we were joining one of these weekly after beer, Friday after beer events in Cologne and Munich, sorry, and we were talking, and she was like, I have this weird source, and I don't know if these rings are for real or not, and I'm really hesitant to publish it with confidence. I would like to have a model of it and would just see if we can prove this with the model, if we can better show this. And I said, well, we can set up a model, you know, these chance encounters we just talk and then. So a week later, I started setting up a continuum model, and our plan was just to make a smooth model of a disk, subtract it from the data, and then see what the residual showed us. If the residual is smooth and basically even, we don't have rings and structure in the data. But if we do see a residual that is ringed or shows any gaps, then we know that there is substructure in the original data. So that was the residual map that I got. There is some sign of rings and gaps, so we could confirm this, but you also see this very weird asymmetry in there. And it just looks like, I mean, for weeks I was scratching my head. I was like, what can I do? I tilted this map. I was like, this is just an angle. It's only probably some type of angling the disk a bit. I tried all parameters. It didn't go away. It stayed. The residual just got worse, but the rings stayed. We still could see the rings and the gaps. And that was before we had gotten the H13CO data that I've just shown you. So if I now show you this alignment, that's exactly the site where the streamer comes in and potentially deposits more material into the disk or injects more material on the disk. After we've seen this, the asymmetry for me at least became a little bit more clear why we see this in the residual image. So that was the smallest scales. Another object that we have studied that was PERM2. This is a younger source than the source I've just previously shown you. This is a binary. Here you see the ALMA 1.3 millimeter continuum image. We have observed this with NOEMA. And in HC3N, we then started to see, or we saw this streamer-like structure on the side of the map. So for the online people on this side. Again, the dotted circle, that's the primary beam of the interferometric observation. So also this streamer extends to the primary beam. So it could extend even further and connect this to larger scales, but we don't know that yet. Is it working? No, it's not changing slides. Yes, now. Here I show you the same I've shown you before. This is the velocity field, and it shows us also this gradient from the outside to the inside in velocities. And we have actually modeled this source also with a kind of streamline model where we just take a parcel of gas, have it free falling, rotating onto the center, and it follows the stream quite perfectly. Now let's jump a little bit scales and let's go to the largest scales, to the molecular cloud scales. This is supposed to be Perseus, but it's not showing up. That's Perseus. This is one of the Herschel Space Observatory images. This is the 250 micron image. Very beautiful image that we got back with Herschel. In fact, Herschel actually showed us that, I mean, this is filamentary, as hopefully you can see with the lights or online. So it's very filamentary structure, and Herschel actually has shown us that a lot of the interstellar medium is very, very filamentary, looking basically like that. Just recently, Azumanian and collaborators have done a very detailed study looking at 8 different molecular clouds that were observed with Herschel. Specifically these 8. They have found in total something like 600 filaments, and they've characterized them and they have calculated their statistics. And what they found is that all these filaments on average have a width of 0.1 parsec, a length of 0.66 parsec, and mass per unit length of 14 solar masses per parsec, which basically for a 10 Kelvin cylinder would mean that these are transcritical. So they're just about to collapse. They are fairly stable. Now back to Perseus. In Perseus, you have many different regions highlighted here that are kind of famous for star formation. These are star formation regions that people have studied for quite some time now. There's, for example, Bana 5, Bana 1, but also NGC 1333. If we look at this a little bit closer, then you can see that the protostars, I hope they did show up here. Yes, the little dots on top of there, these are the known protostars in this region. As you can see, they do line up with the denser structure of this molecular or of the star forming cluster. But what we have to keep in mind is when we look at these column density maps, is these are 2D representations of 3D space. So whatever you might align here as a filament or as an elongated structure or anything might just be a chance alignment along the line of sight, just different structure that are actually not physically related, but are just along the line of sight in the same direction. So in general, the proximity on the sky does not necessarily mean that these are physically related objects. But we do have another mean of looking at these. If we look at these things in molecular lines, we get kinematic information. And with kinematic information, we actually can follow up if material is physically associated or not, or more likely to be physically associated than or not. So what you see here is a great study by Rachel Friesen and collaborators. They used the GBT with the green bank ammonia and performed the green bank ammonia survey. They've done many different star forming regions, one of them NGC 1333. As you can see, the ammonia, the integrated intensity map now follows the column density pretty well. And then Chen and collaborators followed this study up and investigated the velocity field. And they in total found 10 velocity coherent filaments. So every little structure that is here indicated by a letter is one of these filaments or fibers. They are velocity coherent structures, and that's what they found in this paper. Now let's go from NGC 1333 to a different region, BANA 5, and look at it a little bit closer. So this is again the column density map. We have observed this region now with a combination of VLA and GBT data. This is ammonia, the same molecule we have seen before, just a different region. The integrated intensity map of this. And what you see is, no, actually, let me first tell you what's inside. So inside here, what we've known about is this little region that is marked with a star. That's a protostar. This has been long known about. This region contains one protostar. But with these observations, we have also shown that there are 3 kind of dense condensations in there. These are marked by these 3 white dots. And together they form a quadruple system that is in the making. Now, I've looked at this a little bit more. There's a program called Astrodendro that gives you like the isocontours, and you can basically isolate structures within your regions. So I found these 2 filaments, or defined these 2 filaments with this program. Oh, my apologies. And then I used a program that is called FilFinder to just define the spines of the filament. These you see here with these long white lines that goes along the spine, basically. From that, then I was able to determine the filament lengths, which are just 0.24 and 0.31 parsecs. So these are fairly short filaments. Then I decided to define the properties, or like investigate the properties of the filaments in the exact same way that Arsemanian has done this in their study. And what they are typically doing is they take the global filament properties. So let's look at the filament 1. You would just make a cut. This is now starting in the south. It's very hard to see. And I believe it's also very faint to see on your screen. It's much better on mine. But if I keep going, and I keep going with just extracting filament profiles by going along the spine, you see that these that the individual profiles are lining up. You can create an average profile of this. And then what you would do is you would define, well, you have to do some background subtraction just to get rid of everything that's around and only account for the central filament. And then you fit a Gaussian to the center to determine the width of the filament. We have done the same thing. You do the vertical lines, you fit a Gaussian to this and determine the filament width. Another profile that people frequently use to fit filaments is a Plummer function, because this is found to reproduce these cylindrical shapes of what we think filaments are a lot better. So I've also went through this exercise and fit a Plummer profile to this. And now the part comes where we actually compare this to the, what I will now call Herschel-filaments. So I'd shown you some of these properties already. These are the Herschel properties, 0.6, then the exponent, something like 2.2, the widths and the mass per unit length. And here are the numbers we get for BANA 5. So in comparison, the BANA 5 filaments, the smaller ones, they are shorter. They are steeper in their profile. They are also very much narrower. And they have a higher, or they are more supercritical, so they have a higher mass per unit length. So, well, then I asked, okay, can we do something else with the data we have? We have really good quality data that has a very high sensitivity. So normally you do this averaging just because you don't have that good signal to noise, or you need to average a lot of profiles to get the intensity profiles. So I actually went in and did the same exercise I just showed you, but not for the average profile, but for each individual profile. And when you now follow this spine from the south to the north, and you look at, in this case, 3 different parameters, the central density, the exponent, and the flattening radius, these are all parameters that are defined by that are defining the Plummer profile, basically. And then you just go through from the south to the north, and you add one point after the others, you get these spine profiles, basically. Once you have this data, I then started to look for, okay, is there any correlation between these parameters? Is there anything we can find? So I started just plotting them one versus the other. So let me go back, sorry. If you look at the first one, this is plotting the exponent versus the flattening radius. I hope you agree with me. This is a very nice correlation. It's basically they're lining up more or less a nice correlation. I see Jim's face. They are more or less lining up on this line that I fit through here. If you look at the central density versus the flattening radius, that is not that good of a correlation anymore, I must admit. And then if you finally look at the central density versus exponent, that is kind of all over the place. But overall, what you can say when looking at this is that filaments deviate from this isothermal model that we are very often using as they become narrower and denser. Since these are only 3 parameters, and we can actually plot 3 parameters in a nice 3D plot, I did that. And now I hope this is working. And I hope you see the same thing I saw when I plotted these. Those will rotate around. At least for me, they're all lining up on a plane. They're kind of in a plane in 3D space. So then I went in and looked, okay, how can I fit a plane to these 3 parameters? Oh, sorry, I need to stop this. This already. And taking into account their uncertainties. So you have 3 parameters with an uncertainty. I found one package that can actually do this without me having to go through and write this up all by myself. This is Hyperfit. And then I found this correlation by plotting the flattening radius versus the other 2 parameters. And while that is most likely, or this might not be a universal relationship, if we could confirm this relationship observationally in others, we have a nice way of determining one of the 3 parameters by just measuring the other 2. And things like flattening radius and exponent are quotation mark easily measured, whereas density is not that easy to measure and deduce. So that would be a nice way to get the density of filamentary regions. Now let's come back to our overview of the constituents of the process of star formation. So I've shown you that filaments are everywhere. So these Herschel-filaments, you have seen them everywhere. And I've also shown you that we have different types of filament that are actually, or filament/streamers connecting the scales. So something that people are working on is now an updated picture of star formation, where actually you have basically an anisotropic growth of dense structures in the ISM that are then leading to the formation of stars and planets. So you start on the large scales. This is not moving. Now, you start on the large scales with these expanding bubbles that are compressing the interstellar medium and then produce these flattened gas layers in between. From that, you get the molecular filaments, or these filamentary structures, within which then the dense cores are forming. This is on the next one. And from there, we basically go into the same pictures I've shown you, the same stages I've shown you at the beginning, but now just with the added criteria that we do not have this the symmetric infall, but that we have asymmetric infall, and that we have streamers that are forming and transporting material onto the central object that forms. If you ever want to read more, there's the great Protostars and Planet conference that happens every 5 or so years if there's no pandemic. And these are nice review articles for everything in star formation, and specifically for the filamentary streamer things. Jaime Pineda wrote, and collaborators wrote a good review article on this. So how do we proceed from here? Well, actually I should write how do I proceed from here, because my plan for this now is to investigate first the Banner 5 region more, especially the velocity field of this. So I'm in the process of doing a continuum study just to get the general properties of this region better defined and determined. And then the plan is to follow this up by molecular line study to establish database of traces that would allow us to actually trace these different, these filamentary structures. Not every molecule out there will trace the same structure. So you have to look which molecule gives you what you're looking for, basically. Concerning the continuum, we are in a good shape here. So on the very left-hand side in these plots, you're seeing the Mustang 2 data that I've just gotten, I think a year ago. And then archival, the other two are archival Sgr B2 data from the JCMT. And then I run my same routine of trying to set up a 3D model that basically reproduces the observations. So in the middle panel, you see the model, and then in the bottom, you see the residual that we get. But keep in mind, this is preliminary. I'm not having any parameters yet for this. I'm still working on this model. What this allows you to do is, so when you do continuum modeling like that, you get a handle on the dust parameters in your regions. So dust density, dust temperature. And these in turn are important parameters to determine then gas kinematics and gas dynamics, especially if you want to do modeling, you need to know your physical structure before you can actually model your kinematics better. Now I have an insert because I've talked about it a few times or mentioned it. The way I do the modeling is by a framework that I call Pandora. I developed that in my PhD thesis times. And I thought I'd just give you a very brief overview of what it does. So you start with the model setup. You're basically just putting in whatever heating sources you have. If you have none, you have your interstellar radiation field. But in Heimer stars, for example, you have your Heimer stars there that are heating up the environment, so you can place these. You distribute your dust, your electron and ion densities, and you assume molecular abundances if you do continuum molecular line studies. Then you follow this by calculating the dust temperature calculation, or by running the dust temperature calculation, for which I'm using a code that's called RMC3D. After you've done your dust temperatures in your model, you can run the radiative transfer. And then there are two codes that I've employed in this that's called RMC3D and Lime. The difference between the two is, I mean, both can do the continuum. Lime, opposed to RMC3D, will not calculate you the free continuum, just the dust continuum. And then Lime, on the other hand, allows you to run your molecular lines in non-LTE, which RMC cannot do. So that's why I ended up doing two programs basically in parallel, just to have all the options and linking them. Important if you do any radiative transfer modeling and you want to compare to observations is that you actually post-process your data so that they're comparable to your observations. So you're basically just pretending you're looking at your synthetic data with the telescope. In terms of single dish, that's more or less straightforward. Many people just do a convolution with the beam of the telescope and then compare the results. When you have interferometric data, then you have to be a little bit more elaborate. You do the UV filtering and then the imaging basically in the same way you do this for your observational data. And the fifth step is a model optimization. So you can use routines that basically will automatically try to look for the best parameters that fit your data. Additional data that you need when you do all this is molecular data files, opacities. That's lots of data that you need from archives basically in order to actually run the radiative transfer modeling. So that's the framework that we use in the background. Now, I also said I wanted to look at kinematics, and one of the projects we have right now is to look in the Bana 5 cloud again. So you've seen this filamentary part. Now, this is HC3N observations that we have gotten with the IRAM and NOEMA, so the 30-meter IRAM telescope plus the NOEMA interferometer combined. Back then, we didn't know yet about any of this being streamers or being potential filaments and stuff like that. So the whole map extends further to the south and further to the west, but we didn't cover the northern clump. And the spectral resolution of NOEMA only goes down to 0.2 kilometers per second, which for these regions caused that you're only covering it with like 4 channels. you do not really see a lot of the kinematics. Actually, you need higher spectral resolution to really see what the gas is doing. So we have applied, and we're lucky and have gotten GBT time to follow this region up with Argus, and we are going to check if this gas actually comes from this northern clump. So if there's a connection between the northern clump feeding into the filaments or moving more material into the denser region. And we will get a lot better spectral resolution, so we can actually then look at velocity fields. To extend this work long term, it's great to, well, there are two approaches that you can basically do. You can do the bottom-up approach, or you can do the top-down approach. Bottom-up would mean you have a few sources in mind, and you just go from the smaller scales and basically look for how does it connect to larger scales. And top-down is you have a lot more sources, and you just systematically search if you find more of these streamers connecting from large to small scales. So bottom-down is an example. We have talked about iOS 63, or I have talked about iOS 63 at the beginning. This was the H13 CO map. If you connect that to the Herschel column density map and see where it lines in there, I mean, this is a lot lower resolution in Herschel, but potentially this actually might connect to a larger gas reservoir that is located in the north of that disk. And then the top-down approach, what you can do there, should not move. I've also mentioned at the very beginning this study by Osmanian, where they looked at the 600 filaments in these 8 different star-forming regions. And you see a plot of the filament width versus the central column density here. If I were to place Barnard 5 in, I hope you could see that showed up. It's just about here, in this tip of the straight line that they fit. And then you can see that there are quite a number more filaments in these regions that are projected to be very narrow, narrower than the 0.1 that they claim as the universal fit of filaments, but also are very dense. And then one can argue, if one looks at these are regions, it's mainly the orange, the red, and the purple. If you look at and know where these regions are, these are the nearby regions. So they're actually resolved by Herschel nicely. And there could be an argument made that distance with the telescope of the same size affects if you can actually see the smaller filaments or not. So if we follow this up and look at systematically at larger scales, that's actually something interesting to do. And starting points for these are, for example, the gas survey that I've already shown you, where you have a larger area covered with the telescopes like the GBT, where you can start looking into the kinematics of that and then see what are the properties of these filaments. So now Emily has mentioned at the very beginning that I not only do LOMA stuff, but I'm also interested in HIMARS stars. So do we see these kind of streamers like only in LOMA stars? If I phrase it like this, then I potentially will tell you no. So let's look at well, that's our Milky Way. Nice optical picture of our Milky Way. If we go to the very center of this, that's what we call the central molecular zone. This is kind of the inner 200 give or take parsec of our Milky Way. What you see in the top, this is a Herschel Space Telescope 350 micron image. And then I do like very dense things. So the orange dot in here that you find, that is Sagittarius B2, a very famous star-forming, HIMARS star-forming region. If you're interested in finding new molecules, go to the northern dot that you see there. Many molecules in space have been found towards that region. These two dots, so now we are looking at the 250 micron map. These two dots historically are very intuitively called Sag B2 North and Main. If we look further at the main, we have followed this up a while ago with an ALMA band 6 spectral line survey, which ranges from 211 to 275 gigahertz. So basically covering all of this. And now I want to show you just the complexity of lines that you see in here, and I hope this is working. So you should see this moving. Everything you see in the top panel, so the top spectrum, that is extracted towards the dot in this northern clump in this figure. And the bottom spectrum is extracted towards the clump in the, well, wait, sorry. Wait, it's going in the wrong direction. I just want to play this and not move. I just want to show you, as you have a ton of lines in these regions, you have a hard time finding the continuum level in the spectrum just by looking at it. And you see quite a huge complexity. So some of my collaborators, they followed this up. They looked at the continuum, and then they looked at peak intensity maps of different molecules. As an example, in the top, we have Hc3OCHO, and in the bottom, it's H2CS. And I hope you can see that this is very feathery around the central sources. They've also looked at the velocity fields of this, and then determined basically these filamentary or spiral-like structures that moves towards the center of the course. Why do I say it moves towards the center of the course? Because they looked at the velocity, they saw the velocity gradients in there, and then determined the mass flow, basically. What we find is the velocity gradients towards the center of this cluster is between 20 to 100 kilometers per second, which is 10 to 15 times larger than what's typically found in regions like these. And one of the claims that was made in this paper is that Sgr B2n is a good candidate to form actually one of these superstar clusters, potentially. So it has enough mass, it's moving in mass at a high enough rate so that could push it into the threshold of these superstar clusters. Now, Sgr B2 has a ton of observational data. I just show you some here. The top, this is single dish data obtained with APEX, with Herschel, and the different instrument at Herschel, where you see the entire cloud, basically. And then in the bottom, the square maps. These are interferometric maps obtained at different wavelengths with the VLA, the SMA, and ALMA. And then the spectrum you see here on the side. This is actually just a fraction of the large Herschel Hi-Fi line survey that covered basically a terahertz of spectra towards 2 of the clumps in there. If you ever want to look in that, have fun. There's plenty of work to be done there still. What I started in my thesis, but didn't really finish in the end, this is still ongoing work, is something that we wanted to do called, well, we call it molecular tomography. So basically the idea is you have your star class or your cluster of stars at the one end, you have your line sight towards the telescope, and you have this envelope of denser structures in the center and then less dense towards the outside. And along the line of sight, you're looking at, in this case, CO as an example. And what you then see is, due to opacity effects, you're only looking into the cloud for each of the transition up to a certain distance. And then you can basically start seeing, okay, at this, or in this range, the velocity field changes like this and so on. So you're doing a tomography of the line of sight towards the cloud center. What you see here in black, that's the observed spectrum. And I hope it is visible in orange. On top is the result from the modeling. These spectra are not continuum corrected. So the continuum is still in the spectra, and the model fits the continuum very well. We reproduce this, but we still have some trouble with rings of the emission and so on. So these are not perfect fits to the spectra. But if you actually look at the shapes of the profile. So what I'm showing you here is in the top, it's the main isotopologue, CO. And in the bottom of each of these pairs of spectra, this is the optically thin counterpart C18O. And what you see is C18O peaks on the, has a single peak and peaks on the, wait, I have to do this here because the online people won't see it otherwise. Peaks in the dip of the CO emission, which basically tells you that you have a single velocity component. but the double peak comes from self-absorption of the main isotopolog. And then the blue shifted spectrum here and here shows you that you have these infall profiles. And what we reproduce with the model is this change in the asymmetries. So we go from something that is more even in the CO7 to 6 to an infall profile, and then to the stronger infall profile in the 11 to 10 transition. That's basically the idea of the tomography. We can do this for more molecules, but I'm not showing this here. That's a lot of work. And with that, yes, we are coming to the summary. So the filaments, fibers, streamers, there are many terms out there for them. And I think the community is working their way through putting them all in perspective or agreeing upon one term, maybe, hopefully, but probably not. This might form then something like an umbilical cord of star formation, if you want to have this picture in mind, that possibly feeds material asymmetrically from the parental molecular cloud onto the core disk scales. Large-scale, high-resolution molecular line observations are needed to understand the physical, kinematic, and chemical properties. And well, I'm not sure if I've shown you, but radiative transfer is a very powerful tool, but it does take time, especially if you do it in 3D. It does take time, but it is fun to do, and it's nice also to use to connect these type of simulations with observations. That's it. Thank you. Shoot if you have questions.
Yeah, so I'll monitor online. So just if you're online,
wonderful.
raise your hand and I'll call on you, or in any room.
I have a question about the shape model. So whenever you have the models,
Yeah.
you define the shapes by hand, or did you use some sort of clump find?
I initially started by hand. I used contours, so some type of, if you want some type of clump finding, or astrodendro or something where you go with the isocontours, you're trying to figure out where are your densest spots located, started there, and then build the shapes around. From that experience, I would say it should, well, you should never jinx it. It should not be too hard to automate this kind of routine where you use something like clump find, you start putting your centers in, take a guess of the extent, and then have an algorithm that sprinkles the clumps in there and tries to automatically reproduce. I've done some testing on this, but Sgr B2 is a way too complicated source to do this automated. The code just goes insane. I mean, the Sgr B2 model that I haven't shown you here in detail, that has something like 120 components, each of them 3, 4, 5 parameters. It's a complex region. You might be better off with some, well, people said low mass regions, but they are also, because they're so nearby, you resolve them very well. So it's not spherical symmetric, so you run into some other issues. So I haven't yet found a good observational region where one can actually test an automated fitting procedure. But yeah, it's a mixture of by hand and then letting an algorithm determine the rest.
Jay has a question online.
Yes. Jay, shoot. I hope I can hear you.
Okay, thank you. I'm interested in your final comments about molecular tomography.
Yeah.
Do we know enough about the chemistry and the distribution of different molecules that would allow you to do this, not by comparing different transitions of one molecule, but actually by comparing different molecules?
That's a very good question. So normally I would say you would need some chemical model as well, just to get what I've done in the thesis, and what I've found is if you have some higher density tracer than CO, and I had, for example, HCN, then we found that HCN is in the lower transitions, it's infalling, and then if you go to higher transitions of HCN, it starts expanding. And that's when you hit the cluster, the star cluster, and you have expansion motion there already from winds or something. So depending on what your densities are, if one goes with that, with the critical densities, then you can actually do things like that. But I would not say that you can really go in and say it's at 2 parsec in front of the cloud. So I think you cannot really this definitely say how far off, at least yet. And I don't really have a very good chemical model that reproduces your abundances in there. So the abundances in here are all set by hand. which for CO is fairly easy. You have a flat profile, you have no temperature dependence really. Other molecules are more difficult.
We have another question online. I'm not sure who it is.
Yeah. Okay. Yeah, it's me. Sorry. Yeah. So yeah, my question is also related to the CO absorption. So in this particular case, do you is it always the absorption? Can you tell that it's actually infalling faster and faster, like in a free fall?
You mean the absorption here for the CO?
Yeah.
I have not looked into that yet, so I cannot tell you yet if this is inflowing faster. I've not looked at that. What I had in the model was a constant infalling velocity for this part of the inner, well, let's say intermediate scales. So I had several different clumps at different density levels, and this one had a constant infall velocity basically. And yeah, it's a good question. Maybe that would help to get the level of asymmetry, like the ratio of asymmetry, right? But I haven't tested that yet. I will look into it though.
Okay, thank you.
So I had a few. I am not an expert in star formation
Don't worry.
at all. So, but I had a question on the, I think it was the first one, the IRS
63, yes.
So it had just the one filament, I think.
If I do escape now, then you're losing. Sorry, I will share back. Give me a second. You were asking about this one, but this helps to technical parts. Where's my share button? Sorry. Here we go. This one.
So yes, so it has that the upper. It's a filament, right? So that
Oh,
gas
streamer,
is
yeah,
coming in.
Yes.
To
Hit at some point, it hits the disk of the
and
region
then
of this.
continues to form mass.
Yes, or like accrete mass onto the disk structure.
I was
That's
just
at
wondering,
least the
is this
picture.
typical to have it sort of, and then you kind of said it at the end, have asymmetric
Mhm.
formation like this? I'm used to more like galaxy clusters. Where
Yes.
you have a lot of stuff
Yes.
all coming in from different
So
sides.
there are some simulations where they have done the early stages of hydrodynamic simulations, and I believe also magnetic hydrodynamic simulations. And they did see streamers or like accretion streamers, things spiraling in onto your disk structure.
Yeah.
And I believe when Dominique showed this to one of the theoreticians in Garching, they were like, oh, where's the second one? Because they were so used in their simulations to see like either symmetric infalling, which might be due to the way the initial parameters are set, that this was very symmetric. Here, the second one might be hiding. Or if you remember the picture I showed you of the larger scale molecular structure of Eucos in that area, where you just had the material in the north, and there's just nothing really in the south that provides enough inflow. This, I don't know yet.
So is this kind of the first time this was seen, or have other people seen this
The
as
very
well?
first one, at least that's seen and reported as something like that.
Yeah.
That was the Perm 2, to my knowledge. After that, more people came up and say, hey, we see this as well. We see this as well. We have always ignored this, or this was in the data for a long time or something. And people have just probably not paid that much attention to these intermediate scales that basically link the structures. So I'm assuming it had been there all the time, and we just didn't pay really a lot of attention to it, just focusing on, hey, let's go to the disk and let's look at, or let's go to the next higher resolution stage that we can look with the next big telescope we get. So, yeah. But I'm assuming actually a lot of this is quite similar to what you also see physics-wise, probably.
In the high mass world, Patrice shows some ways that has a survey with ALMA on high mass star formation. He sees these one-sided streamers all the time, and occasionally a two-sided.
Okay.
Occasionally.
Has he
More
connected?
often it's
Yeah.
one-sided than two.
Has he connected them to like larger structures and how these
I don't
regions
think so.
relate? That would be interesting
That
to
would be,
see
yeah.
if there's like just material only on one side, or if it is distributed throughout.
And just as an added teaser, the magnetic field goes right along
Okay.
the fronts.
Okay. Yeah, think for these we do not have the magnetic fields, but I might be wrong. I'm not a magnetic field expert, and I don't have the
Should be
overview
very
of
fun
it.
to see.
Yeah.
I had a question about your
Yes.
filament widths.
Yes.
I remember many years seeing a talk, they said all filament widths are 3 times the resolution of the telescope. It's just an effect of the
Of the
filament width finding
Yeah, yeah.
algorithm. How does your width compare to the angular resolution of the telescope?
good question. I'm trying to think the numbers through. 1 point. No, I'm mixing up. I will go through that number. I'm not doing this out of the top of my head. I will get them mixed up, but I will look at it with factor of 3 and if that could
Yeah.
play
But
a number.
You did make the point,
Yeah.
that the more massive, presumably the more
Yes.
distant ones have thicker filaments.
Yes, and then it would be a
This is all
resolution.
angular
It could
resolution.
be. That's a good point. I mean, not all of them, but yeah, the ones varied where, at least in the Armenian sample, we saw that they are narrower filament. These were predominantly colored in the nearby regions. So yeah, that made me a bit, why? But yeah, good point. I will look into that.
And one last question, the correlation you have between the flattening
Yeah.
and the steepness.
Yeah.
Is that just, how would you expect them to be related naively?
That's a good question, but I thought about this, at least if this is some residual from the fitting, or if this is something that could be introduced by the fitting. I do have to share again because I'm always losing the sharing when I do this. I should probably just share the entire screen or something. My apologies. So what I did is I just produced artificial spectra basically by just putting in the parameters and then see what the algorithm of running through would actually find. Would it find the same that I plug in or similar? And what you see in the black is what I basically put in. The green shows where I fit them, but these are, yeah, it looks like a large spread, but I'm actually doing violin plots. And you see where the major part of this is. So there are very few that deviated quite a lot of these many things I did. And the majority of them, I should show this here because online, in the, they fit nicely along the page. So we are actually,
You subtract off some sort of
Yes.
large scale
Background.
background. Is there any
Yes.
relationship between how your parameters scale and your background?
not that I thought of, no. I have done the background subtraction also, or like adding noise to these as well. Yeah, no, you want background.
If you have a bump on top of a big background, that may be different than a bump on top of a little.
That's a good point. Yeah, for B5, it's luckily so nicely isolated that
B5, you're
you
probably okay.
pretty much have a like flat background throughout and don't see much around it. I remember, at least in the appendix of the Armenian paper, she had done an extensive study on background emission, if I'm not mistaken right now, because she had this problem, or they had the problem in their analysis that everything's so crowded that you really have to be sure that you're properly taking off background and not how much background affects. But I don't remember out of the top of the
I
head
agree,
the
B5 is
conclusion.
probably okay.
Yeah. Okay. There were more questions. Sorry, I'm pointing in all directions now.
I was curious about the,
Yeah.
the streamer you showed.
Yeah.
Do we know what's the 3D geometry of this?
The full 3D, no.
It would have to be pointed away from you though.
Yes. So it goes back behind and comes in, but I don't have the exact 3D. Wait, now I will do a different sharing so that I don't have to go back and forth and the online people see me in between and not. Let's do it like this. And I can actually, so this is the, let me remove all the stuff around so we see more. That's a bit better. And that's a bit better. Hopefully now it's kind of big enough. So that was the streamline model that Jaime basically fit. So what you do is you have some type of parcel of gas that goes free falling onto your center and it's rotating. And then it predicts you what gives you the velocity and the location. And you plot this in orange on top. And from this, you kind of see that it is going behind and then comes back in on the side. But the exact, we do not have like a 3D representation of the whole thing like I do have it in my modeling or so. We haven't done that. But yeah.
It looks like a very nice disk velocity field as well.
Yes,
around
the
this.
Keplerian disk. Yeah,
How big is that disk?
I should know. I should know, but I don't out of the top of my head.
So is it the size of an Oort cloud, or is it a few hundred AU across?
Mm, oops.
There you go, it's 500 AU.
Yeah. Give or take. Sorry. And that's the gas disk here. The dust disk is much smaller, like 100 or something. Yeah. You, yes, next.
Slide with first one. I just wanted to know how you figure out the exact position with the star formation location.
The which sorry, which slide?
I don't know. I didn't take note of the slide because on the first one.
I'm not sure which. Sorry, can you just repeat again? I don't know where to go.
On the first survey.
And the
Where there
gas.
was a molecular cloud and there was white points showing up.
Ah,
the
these
location.
dots here.
Yeah. How did you forget the exact location of this?
These come from the dots. They come from I believe no, not Weiss at this time. This is Dunham. So this is IRIS survey or not certain. This is an infrared survey basically. Or
Yes,
Spitzer.
there was like a special survey.
Yeah, there was a different, so I should have added this here. That's coming from a different data set, and you basically then see the protostars in there. Very, very compact emission, and with that,
Mid-infrared point sources.
Yeah, yeah.
Mid-infrared point sources.
so that's a different wavelength. This is not based on the continuum from Herschel, different data set. And that's where the dots come from. And then you have their coordinates and plot them on top here.
Any final questions?
One more.
Is there a lower limit on the massive low mass stars that have these streamers?
Maybe, we don't know because we do not have enough samples. I mean, there's not enough. I mean, I think my collaborators start building up some type of, if you want, database or something. You can still count them. I would say by hand, probably by now, maybe 20-ish. I don't know how many there are. People start looking for them, so more and more show up. But I think it's not enough yet to actually have statistics. Yeah.
It's a great question.
Yes.
Do brown dwarfs form this way, or are they always formed in the disks?
Good question.
Disk
Yes.
instability?
What's the origin of the filament?
The origin of the word, that's a good question, actually. It's not a dumb question. I should know more about this. Debated, I would say. So if we have then Jim, what's your interpretation for that?
So gravity always works fastest along the shortest axis.
Yes.
So that tends to pull things into filaments. So, you know, the theorists who start with supersonic turbulence, you get flat things, and those flat things intersect, and that voila, you have a filament. But it's really the collapse. It's the same reason you have a cosmic web. The short axis collapses faster than the long axis. Yeah, so
Yes.
you're colliding
The
forms are your
colliding
first rush.
Probably multiple ways depending on your conditions around and your structure.
But it is ubiquitous.
Yes.
Nature has found a way.
All right.
We're up on
At the
time.
hour. Wow.
Thank you again, Anika.
Thank you, everyone.